Thank you so much, Shannon. I appreciate all your help. Welcome everyone to our 2023 NOAA Fisheries EBFM seminar series. This is the last one of December 23, and we will continue into 2024, and we'll talk about that a little bit. Thank you so much for joining us, and I just want to acknowledge all the past speakers. In this particular year, we turned out to be the top most popular seminar series at NOAA this past year, thanks to Shannon's support and all of the NOAA library folks who have helped us out with this, and also all the speakers that have contributed to this year's series. The library continues to be such a valuable host for us, and we offer these every second Wednesday of the month from 3 to 4 Eastern Time. Each presentation is accessible and archived by the library in their YouTube linkage, and we can provide that information to you later. We are so lucky today to have Dr. Jamison Gove from our Pacific Islands Fisheries Science Center. He's going to be speaking today about the ecosystem status report for the Hawaiian Islands, and we are very anxious to transport ourselves out to Hawaii and enjoy his presentation. We do have a speaker scheduled for January 10th, 2024. Hard to believe we're saying that already. Dr. Howard Townsend, who is from NOAA Fisheries as well, and he'll be talking to us about the latest in terms of National Ecosystem Modeling Workshop and some of the models that are being worked on with respect to climate-ready fisheries management. So please join us again in January, and I'll turn this over to Jamie. And thanks again so much for all your work on this, Jamie. Appreciate it.
Yeah, thanks, Peg, for the introduction. And aloha, everyone. Good morning from the North Shore of Oahu. My name is Jamison Gove, and I'm an oceanographer with the Pacific Islands Fisheries Science Center, and I help lead and coordinate the Hawaiʻi Integrated Ecosystem Assessment. Before I begin, I really just want to say thank you all for attending this seminar. Life is super busy, and time is an extremely limited resource, so I fully appreciate you taking the time to be here today. So I want to begin with a brief roadmap for today's seminar. So I'll start off by providing a somewhat protracted, but certainly relevant and hopefully interesting introduction. I'll briefly mention our transition from West Hawaii to Hawaii. I'll then get into really the meat of this presentation, and probably why you're all listening in today is our ecosystem status report for Hawaii, and I'll end with some key takeaways. So there's a lot of super cool and fun facts about the Hawaiian Islands that we could talk about, but I wanted to highlight just a couple that are relevant for marine ecosystems and I think provide some context for today's talk. So there are really large variation in elevation in Hawaii, and that's both above and below sea level. And that drives a lot of the oceanographic and ecological dynamics that we see. So a good example is Mauna Kea. It's the tallest sea mountain in the world, and actually if it's measured from the sea floor, it's the tallest mountain on the planet. In terms of rainfall, we have really large variations in rainfall, some areas as low as 8 inches a year, and Mount Waialeale, which is on Kauai, receives up to 450 inches a year, which is, depending on the year, is one of the wettest places on Earth. And in terms of waves, we see really large waves seasonally, regularly exceeding 40 feet, sometimes as high as 50 feet or 15 meters. And that's arguably the largest and most powerful surf of any tropical island chain. Now, I want to briefly zoom out for a minute and highlight another important point about Hawaii's biogeographical setting. So this is a map. It's a map of surface chlorophyll, which is a proxy for phytoplankton biomass. More phytoplankton generally means more primary production, and as most of you probably know, phytoplankton production is really an essential energy source in the ocean. It drives marine ecosystem trophic structure and really dictates global fishery yields. These deep blue areas, these represent really low levels, some of the lowest levels of chlorophyll. And I want to highlight that Hawaii sits right in the middle of one of the largest low chlorophyll regions in the Pacific. But when I think of Hawaii, I think of coral reefs, which are highly productive ecosystems with colorful reef fish, roving predators, and large schools of coastal pelagics. I also think of pelagic fishes like mahi and billfish. I also think of large megafauna, and I think of a high abundance and diversity of cetaceans, which includes pilot whales and Fraser's dolphins, and yes, even orcas. Actually, orcas were in the news recently. They were spotted locally on off West Oahu, and all these photos were actually taken from the recent Hawaiian Islands Cetacean and Ecosystem Assessment surveys that just wrapped up last week. So thanks to them for these great photos. And for those of you that know me, you would assume that I would also have the North Shore and surf high on the list of things I think about, which is absolutely and totally true. But I also think about the rare surfing humpback whale, mostly because I was standing on the beach at this moment when these humpbacks actually came into the lineup and surfed this wave at Pipeline. And it's probably one of the craziest and most memorable things I've ever seen. But all that to say, the point is that the Hawaiian Islands are really hotspots in ecosystem productivity, which is somewhat of a paradox, given that the island chain resides in low productive or oligotrophic waters. But because of island interactions with ocean currents and winds, we have upwelling, we have mixing, we have internal waves, we have rainfall, and all those mechanisms, what they do is they inject nutrients into the euphotic zone, which fuels increased phytoplankton production near the islands. And that increased production, it elicits all sorts of ecological responses that propagate really throughout the food web. So a couple of examples are, we have open ocean fish species like tuna or billfish or mahi. These become island associated because they're queuing in on these increased food resources. Insular and pelagic ecosystems become strongly coupled, they're strongly connected. We do have a high abundance and diversity of cetaceans in coastal waters. And we also have pelagic and deep sea and coral reef fish larvae all co-occurring in surface nursery habitats near these islands. I bring this up because I think it's really important within the context of thinking about ecosystem-based management, is these boundaries, these delineations that we place on ecosystems, whether that's state and federal waters, whether that's thinking about coastal and pelagic research studies and management, they're not necessarily well suited for managing island ecosystems. And that's because of this fluidity and this interconnectedness among ecosystems. Well, these strong connections between pelagic and coastal ecosystems and between land and sea, these connections were deeply rooted in Indigenous Hawaiian stewardship practices. Indigenous Hawaiians really long understood these connections and actually practiced integrated ecosystem-based management. As an example, the Ahupua'a system, it encompassed the entire valley or the watershed, and it stretched from Mauka to Makai, or from the top of the mountains down to coastal ocean waters. And this really influenced everything from freshwater use to what was planted and harvested, including fishing restrictions based on species and the timing of spawning. The Ahupua'a system was nested within a larger social ecological region or a biocultural district called a moku, which provided a scalability, basically a scalability from local to more regional management. And I point this out because there's really a lot of overlap in historical Indigenous stewardship practices here in Hawaii and our current push or shift towards ecosystem-based management. Changing course for a bit, I want to narrow the focus here on our own history. Previous ecosystem status reports in 2016 and 2019 were largely focused on West Hawaii, which is the west coast of the Big Island, as you can see on this map to the left. And this overlapped with the geographic extent of the Integrated Ecosystem Assessment, which is the program that produces the reports. There was a lot of great reasons for us focusing on that geography. First and foremost, there was a lot of overlapping federal and state efforts. So there's the Humpback National Marine Sanctuary has waters in West Hawaii. It's a priority area for the Coral Reef Conservation Program as well as the state. It was a habitat focus area. There was lots of existing spatial marine management areas, lots of active fisheries, and really importantly, a highly engaged community, which has really shaped a lot of the directions that the IEA has taken, whether it's indicators or other pursuits. But based on scoping meetings and conversations with the council and the regional office, state managers and other stakeholders, it was pretty clear that we needed to expand beyond West Hawaii. Basically, there's management needs that the state and others were interested in. And so the first thing we did in this change is we changed our name, which fortunately was an easy one and an early win in this transition. Everything else has been slightly more of an undertaking. That's because we went from focusing on one side of one island to all sides of 8 islands, which is about a 7.4-fold increase in total coastline. So pretty large, substantial, or really large spatial expansion. And while previous reports did include offshore waters and pelagic fisheries. They were largely focused on coastal ecosystems. And so this report, as we'll see soon, actually includes data from the entire EEZ, which is slightly larger actually than the total area of the West Coast EEZ. So suffice to say, we've had some strong growing pains. But I'm super proud of the ecosystem status report and am excited to present on it to you today. So without further delay, I'll present a couple of highlights. The report is broken out into 6 sections, and we'll just present, or we'll talk about just a couple of indicators from each of these sections. I'm going to first start with human connections, because a really important point is that the vast majority of people in Hawaii live near the coast, and that results in strong connections with the ocean and ocean ecosystems. And here's a map of human population in 2020. And you notice most of the colors are all coastal. And so 83% of residents in the Hawaiian Islands live within 5 kilometers of the shoreline, and 94% live within 10 kilometers. So again, most people in the state really live near the coast and near the shore and near the ocean. The National Core Reef Monitoring Program conducted a series of socioeconomic surveys of residents in Hawaii, and the surveys were really extensive and provide a lot of useful information about people's connections with the ocean. And so we worked with Mary Ellen and others from the NCREMP team and present just a couple of relevant highlights from their surveys within our ecosystem status report. One of them was on resource use, and a couple of highlights from that are really a lot of people, nearly 80%, visit and hang out on and spend time and recreate on the beach. And I failed to mention that the population of the Hawaiian Islands is 1.5 million people. So that's quite a lot that are actually visiting the beach. And I think that this number is pretty interesting, is that over half of residents snorkel. So they put on a mask, they put on a snorkel, and they put their face underwater and look at what's going on. And a third of all residents fish or participate in some sort of fishing activity. When asked about their perceptions of the status and trends in ecosystem indicators, such as water quality or the amount of live coral or the number of fish, the perceived status of each indicator varied. Some perceived as good as rather than bad, and vice versa. But the majority of residents perceived negative trends in all of the indicators, which makes the point that if the NCREMP surveys are representative, which they are meant to be, most people think that certain aspects of ecosystem state are declining over time. And I think that's actually a really important point within the context of thinking about moving forward with ecosystem-based management. I'm now going to shift gears to our next section on small boat commercial fishers. We focused on small boat fishers, say, instead of commercial longliners for a number of reasons. First, and I think foremost, is there's really comparatively high participation. So upwards of 1,600 small boat fishers versus just under 150 active deep set longline vessels in 2022. So there's a lot of people that are participating in this fishery, and those are individuals that are in the community and supporting the community. These fishers have really diverse and overlapping motivations, whether it's commercial, recreational, or cultural, and those are really important for local food systems and social cohesion. These fishers often deploy a range of gear types and catch a variety of target species, and overall they represented about 12% of all commercial catch in 2022, which is not a large amount, but certainly not an insignificant amount either. And finally, we focused on this in part because of conversations with the council and their interest in looking at small boat fishers and their catch. While the fishers may switch between targets, we ended up splitting fisheries kind of into these natural 3 fisheries: near shore, bottom fish, and pelagics. And for the sake of time, I'm only going to focus on indicators related to the pelagic fishery, which is by far the largest proportion of catch, but also has the highest fisher engagement and pulls in far more revenue than the other fisheries. For all fisheries, we collated data from 1990 to 2019, which is 30 years prior to the onset of COVID. We did this because when we started our analysis in 2021, the impacts of COVID to fisheries were really just being evaluated and understood. It was clear, or it seemed clear at the time, that those impacts were basically still ongoing. So rather than misrepresenting or confusing things, we just decided to punt and include it in subsequent reports. And so this graph on the top left, this is annual catch over 30 years for pelagic specifically. Note that the shaded region in the panel is basically just a zoomed in version below of billfish and other pelagics. And other pelagics represent catch of mahi and ono, which is wahoo and opa, and a couple of other fishes. And that's just so we can see those trends over time. So quite clearly, we see that tuna is the vast majority of catch, which has actually seen over a 50% decline within the time series, with the peak being about the mid-1990s compared, and that 50% decline comparing it to later in the time series. Looking at catch per trip, though, the story is not as dramatic, although declines are clearly seen in tuna and billfish. But interestingly, we do see that catch per trip, this is the graph in the lower left, has increased for other pelagics over time. Looking at temporal trends in pelagic catch, I think really only tells us a small part of the story. So we're interested in looking at spatial changes in catch over time. And so we looked at changes in catch by commercial reporting block across the Hawaii EEZ, or economic exclusive zone, excuse me. We did this by comparing the average catch of pelagics over the most recent 5 years the catch of pelagics over the most recent 5 years and compared that to the historical 25-year average. And so here's a legend on the lower left where blues are an increase in catch and reds represent a decrease. What we find is, despite what I sort of just mentioned, is that we have this overall declining catch. There are areas that increased in catch compared to the historical average. So east of Kauai, north and east of Maui, as well as parts of the Big Island. But as you would expect, many areas actually show a decrease. All of Oahu, there's some pretty dark reds around Oahu, Molokai, and other parts of the Big Island. And in fact, about 75% of coastal reporting blocks, and these are these sort of amorphous polygons around each of the islands, showed a decrease. Now, there's likely many factors that contributed to these spatial changes in catch. We do know there's a 16% decrease in fisher participation over the time, for example. But I would just say that determining what other social or climate-related factors might be important is an active area of research for our program. In addition to fishing, there are really many other pressures that are relevant to fisheries management and relevant to ecosystem-based management in Hawaii. And this is because the vast majority of human activity takes place in and adjacent to the nearshore environment. So for example, looking at coastal infrastructure, this is a photo of Waikiki, which has large amounts of concrete and impervious surfaces right along the coast. Wastewater pollution, which is a big issue in Hawaii. This is a map of all 88,000 cesspools we have in the state. And you'll notice that the vast majority of those are very proximate to the ocean. We have land use and land cover, which can lead to soil erosion and sedimentation. This is a photo of a fence line running down the middle. On the right is clearly a denuded landscape, which is open and unmanaged and really has quite a lot of feral goats that roam around and pretty much eat everything in sight. Whereas on the left, this is a fenced area to exclude those animals. And so those differences, particularly on the right, can lead to really large amounts of sedimentation entering our coastal waters. And while most of our issues are chronic, there can be acute disturbances. For example, this military plane recently slid off the runway just a few weeks ago in Kaneohe. Unfortunately, no one was hurt, but the damage to the reef was, as I understand, quite extensive in that area. So minimal spatial area, but large impact where it happens. The combination of these land and sea-based human pressures results in cumulative impacts to marine ecosystems in our region across the state. And led by Joey Lucky, who used to work with the Hawaii IEA, but has now transitioned to the regional office, we ended up quantifying spatial variation and cumulative impacts for Hawaii, for all Hawaiian Islands, which is really the first time that it's been done. And this is a map of cumulative impacts, and it definitely doesn't do the data set justice. And so what I'm going to do is I'm going to navigate to the IEA website, which actually has a viewer where you can view and zoom in to the cumulative impact data set. So I'm going to switch screens. Okay, you should be viewing a map, and this represents the cumulative impacts. And I think the interesting thing, I'll zoom in, and we're looking at Oahu. The cool thing about cumulative impacts is it really clearly, where I guess I'll just say that the dark reds and purples are really the highest scores of cumulative impacts. You can really see spatial variation in where we see the most human pressures or the most cumulative impacts. But I think what is really interesting is that you can have different reasons for high levels of cumulative impacts, and so the underlying drivers of ecosystem change might vary from place to place, even though they have high impacts. And I'm just going to juxtapose Honolulu and Waikiki and compare those cumulative impacts with what's happening on the North Shore of Oahu. Waikiki, Honolulu is obviously a large and a really populated urban area, whereas the North Shore is a bit more rural. And so they both have high cumulative impacts. And so I'm just going to zoom in, at least to the North Shore for now. And I'm going to turn off the cumulative impacts, but I'm going to turn on the on-site sewage disposal layer, and specifically looking at nutrients. So in this area, there are a lot of cesspools, and the cesspools leach a lot of nutrients. So we could see in the watershed, a lot of those nutrients reach out to the coastal environment. And because of land use and agricultural, there's also a lot of sedimentation in this area, as we can see from this layer. But because it's more rural, there is really not that much urban runoff. And we'll clearly see that as we zoom out and shift towards Waikiki and Honolulu. So we can see the levels of urban runoff are really quite high, and that's a major contributor to the cumulative impacts. And that's because all this concrete and all of these impervious surfaces, anytime it rains, it just exports stuff straight to the coastal ocean. And because there are some wastewater treatment plants in the area, we do have really low levels of wastewater pollution and nutrients, again, unlike what's happening on the North Shore. And we can kind of play with this all day, and I don't want to spend any more time on this, but we will share a link to this viewer so you can explore all the Hawaiian Islands and look at each of these individual layers, as well as there's a whole series of explanations of how we came about these layers and different links to different data sets. Okay, so we should be viewing the presentation again. Let me just double check. Yep, okay, moving on. So as I mentioned, as we were navigating it, mapping cumulative impacts helps really home in on the areas that receive the highest levels of stress, but I think, understanding the individual data layers underneath it help provide specifics on the likely underlying drivers of ecosystem change, and I think that really helps formulate targeted management. And lastly, before we move on, I just wanted to point out that cumulative pressures are explicitly called out under Guiding Principle 3 in the current version of the ecosystem-based fisheries management roadmap. And specifically, it says identify the individual and cumulative pressures that pose the most risk to those vulnerable resources and dependent communities. And that is largely what we have tried to do in our impact mapping. Relevant to cumulative impacts in coastal ecosystems would be coral reefs and reef fish. So we're going to move on to indicators for this ecosystem. And fortunately for us, we have the National Coral Reef Monitoring Program for the Pacific located in our Science Center. And specifically, I was able to rope in Ty Kittinger and Courtney Couch to be co-authors on the ecosystem status report and really help shape this section. So NCREMP does a lot, far more than we could cover in our report. And so we focused on 6 indicators, 3 for reef fish and 3 for reefs. And they're all presented in a very similar manner in the report. And so here's an example of reef indicators, which shows both the spatial and temporal change across each island. And there is a lot going on here. I fully realize that. So we're going to zoom in on a single island to really help walk us through things and help understand this figure. As part of the survey design, NCREMP surveys by sectors. And so in this case, this is the big island. There are 4 contiguous sectors that circumnavigate the island. The sector color, this is the blue color round. This is the average coral cover for the survey timeframe, from earlier to more recent, as we move from closer to further away from the island. So for West Hawaii, or along the west coast of the Big Island, coral cover was about 30 to 40% in earlier surveys and is now closer to 10 to 15%. We also included the direction of change, represented here by those bars that are running perpendicular across all years for each sector. And this bar determined whether coral cover was increasing or decreasing or showed no significant change. And again, using West Hawaii sector as an example, we can clearly see that coral cover was decreasing as shown by the red bar. Finally, we wanted a way to provide the current status of a given indicator and contextualize that status across all islands. So we compare coral cover from the most recent survey for a given sector to all sectors for that survey year across all islands. And this is represented by that colored dot that you see, whether it's high, medium, or low. And again, looking at West Hawaii, we can see there's a green colored dot, and that means that for 2019, coral cover in West Hawaii was high compared to all other sectors. The gray sectors, these are basically just years that we were unable to survey, or the NCREM team was unable to survey those sectors. So now pulling back to all islands, but I still want to just focus on coral cover, is I want to first note that, like I just mentioned, is that not all sectors were surveyed for each year. And that's because the Hawaiian Islands are big, and it's just tough to get a high enough sample number in each of these sectors to say anything. The NCREM team is going out to sea this summer. So if anybody has controls or input on ship time, this is a plug for them to get some additional sea days to fill in some of these gaps. But back to this, regardless, we can talk about some general findings. We found that about 30% of sectors decreased over time, but about a third of all sectors from the most recent survey actually had relatively high coral cover. So for example, North Lanai and Kaho'olawe, they had as high as 30 to 40% coral cover. Some of the lowest coral cover was actually in Niihau at about 1%, which Niihau just gets absolutely hammered by northwest swell every winter. So it's unsurprising that it would be difficult for corals to grow there. For the sake of time, I am going to move on. But again, we also have other benthic indicators and indicators of reef fish. And so if reef ecosystems are your thing and you're interested, please feel free to dig into our ecosystem status report. And also NCREM has all sorts of great products and information on these data sets and their findings. So I'm going to shift gears again now to talk about climate and ocean conditions, which really can be highly variable in Hawaii. You can have local scale variation in exposure to currents, upwelling, wind, wave forcing, and these are all superimposed on a backdrop of a changing climate. Sea level rise is increasing erosion, and coastal infrastructure, such as hotels and this house, are at risk. Rainfall events are increasing intensity, which can flood entire towns, like this event in Haleiwa town in 2021. And when combined with land use changes, we can have increased sedimentation, which can result in poor water quality in coastal ecosystems, which is both an ecological and a human health concern. So suffice to say, Hawaii is dynamic and conditions are changing, which does have massive ramifications for fisheries and ecosystems in the region. I'm going to focus on rainfall for a sec. We know from the literature that average rainfall is steadily decreasing across much of Hawaii. As shown with this map, the yellows and reds and oranges, these represent decreases, and this is in percentage of decrease in rainfall per decade. So knowing that, what we did is we instead focused on changes in peak events. In this case, we calculated the percentage of annual rainfall that occurs in just the top 5 days of rain at each of the major airports for the last 30 years. So, for example, in some areas like Hilo receives about a fifth, 20% of rain in just 5 days. Whereas other locations like Honolulu or Kona, upwards of 30 or 40 or even 60 to 70% of annual rainfall can occur in just 5 days. So that's a lot of rain in a very short amount of time for these areas. And comparing the most recent 5 years to earlier in the time series, we can see that Honolulu, for example, which is in the green, the proportion of rain in peak events has increased by nearly 80%. And if we think back to the cumulative impacts, there's high amounts of urban runoff. When you combine large amounts of impervious surfaces and lots of rain, you can get really a lot of transport of toxins and other things to coastal waters. So ultimately, so what things are changing is when it rains, it seems to pour. Speaking of coastal waters, we wanted to include an indicator that reflected the consequences of peak rainfall events to ecological and human communities. And so we worked with the State of Hawaii Clean Water Branch to collate data on brown water advisories. And the state issues a brown water advisory when water is, you guessed it, it's when it's brown and potentially dangerous to human health. And basically this photo is, there was a brown water advisory issued during this event. It usually occurs when there's heavy rain and excessive runoff enters the ocean, and that runoff, like I mentioned, can contain all sorts of things: pollutants, metals, virulent bacteria. And so what we did for our indicators, we calculated the percent of year in which a brown water advisory was present within a given region over the 2018 to 2021 timeframe. And that timeframe was just based on data availability. Some general patterns: windward facing coastlines tended to have more advisories, and that makes sense. Windward coastlines tend to get more rain. Some regions had an advisory present for upwards of 40% of the time, and I was actually pretty surprised by that. I will say that to have an advisory, for that value, it doesn't mean the entire region needs to be under a brown water advisory, but some portion of that region has a brown water advisory. And overall, Oahu, unsurprisingly, had the most advisories of all islands. I'm going to shift now to looking at temperature. And what you're looking at is monthly sea surface temperature for the past 120 years in Hawaii. The red line is the 12-month moving average, and the dashed lines, these represent plus or minus 2 standard deviations. A couple of things: Hawaii clearly has a seasonal and interannual component of ocean temperatures, and that's a confluence of the Pacific Decadal Oscillation, influences of the speed of the North Pacific subtropical gyre, and to some extent, albeit a lesser influence, the various phases of ENSO. But noticeably, there is a clear and increasing trend in ocean temperature, with recent years being particularly warm. So using the satellite record, we can estimate that warming to be about 0.15 to a quarter of a degree Celsius per decade over the last 3 decades. But question: what is this ocean warming? What does this warming mean for ecosystems? Historically, the main Hawaiian Islands had mostly been spared from large-scale coral bleaching events, but this really all changed in 2015. Here's that same historical record, but note that the 2015 event clearly stands out over that record. Here we're looking at SST anomaly from 2015, highlighting that this was really a large-scale event across much of the Pacific. And I also believe this is the event that we were gifted this term, the blob, which became a regular part of our lexicon. And that's referring to the large warming that was in the North Pacific. This lower right map, this is a map of maximum heat stress using a metric called degree heating weeks. Darker colors in this map represent more heat stress, and I'll just point out that a value of 8 or more is expected to cause widespread coral bleaching and mortality. And in fact, Hawaii did see substantial bleaching and coral death, and one of the hardest hit reefs, one of the hardest hit areas was West Hawaii's, which makes sense based on this thermal stress map. And in some reefs in the region lost 50% of total live coral cover, so some pretty substantial declines. So as we think about future warming, 2 questions come to my mind anyways, is when can we expect ocean temperatures to cross some critical threshold in which severe bleaching would be a regular occurrence? And a second one is there anything we can do about it? So working with collaborators, Ruben Van Hooydonk and Jeff Maynard, both co-authors, and Jeff helped co-lead this report, we downscaled the current generation of climate models, or CMIP 6, to 5 kilometers. And we estimated the year at which ocean temperature is expected to reach 8-degree heating weeks each year from then on. And so what we call this is the onset of annual severe bleaching. And this figure is for the fossil fuel aggressive scenario, or SSP 5 8.5. We found that the average across the main Hawaiian Islands was 2048. But as you can see, there's really large spatial variation in that year. There's actually roughly a 30-year range, with some locations really having decades more time to adapt and acclimate to ocean warming than others. But still, there's a lot of red, which is the early to mid 2030s, which feels very soon for these areas to reach this threshold. So back to my second question, what can be done? Well, global climate policy could be enacted and really gain momentum and start to cut greenhouse gas emissions. And so to estimate the influence of climate policy, we compared two scenarios. We compared the scenario I just showed, which was the increased fossil fuel use scenario, and the scenario that assumes effective implementation of global climate policy to reduce carbon emissions. And this is SSP 5-4.5. And so this map essentially subtracts those two scenarios, with the values representing the delay in years of the onset of annual severe bleaching. So the short story is the differences range from 0 to 28 years, with much of Hawaii gaining a decade or more of time. And those are not trivial timeframes for these ecosystems. And based on this reduction, based on climate policy and a reduction in global carbon emissions. But the reality is, most of us are not directly involved in writing global climate policy. If we were, we'd be in Dubai, and it'd be very late for us right now, and we probably have more important things to do than attend my seminar. But many of us might be involved in supporting or writing local policies, which can make a difference, even under ocean warming. And we actually show that local management matters in a recent publication in Nature. And what we did is we took many of the data layers from the ESR, tweaked them a tiny bit, and in collaboration with a number of academic partners and NGO partners, including managers from the Pacific Islands Regional Office, the state of Hawaii, as well as the National Park Service, we looked at the importance of local management in determining coral reef outcomes. For example, we looked at long-term monitoring of reefs, and this is from West Hawaii specifically, and we showed that some reefs actually increased in coral cover over time, shown by the blues, and others decreased, shown by the reds. And we're interested in really why, what are the set of circumstances that would lead to that? And so we looked at the differences in human and environmental drivers between these positive and negative trajectory reefs. And what we found is that reefs with positive trajectories had far higher fish biomass, particularly the biomass of herbivorous fishes, and these are browsers and scrapers and grazers. But those reefs also had really low levels of land-based stressors, so really low levels of urban runoff, low levels of wastewater pollution. And alternatively, the reefs that decreased over time had far less fish biomass, very little herbivorous fishes, and had much higher land-based stressors. So continuing on this theme, this is the distribution of reef builder cover 4 years following the marine heat wave. And reef builders are basically a combination of corals and crustose coral and algae, and they're really essential for coral reef accretion and growth. And importantly, they represent an indicator for reef recovery potential following an acute disturbance or following something like a really devastating marine heat wave. And so our first step was we looked at the primary factors that determined whether reef builder cover was either low or moderate or high 4 years post-disturbance. And one of the most important factors was actually the amount of herbivores known as scrapers. Scrapers are primarily parrotfish in Hawaii, and these guys literally scrape the reef when they're feeding. And those scrape scars, what opens up space and, in short, promotes coral reef recovery following an acute disturbance. Another, and the second most important factor was wastewater pollution. And wastewater pollution contains toxins, pathogens, and all of that can increase coral disease, reduce coral growth and reproduction, and increase coral susceptibility to bleaching. As I mentioned before, many of our 88,000 cesspools in Hawaii are within just a few kilometers of the coast, and so there's That water's easily gets in the groundwater and easily gets to the coastal waters. We were then interested in modeling management scenarios. And those management scenarios were either sea-based, which is essentially fisheries policies that promoted scraper biomass, or land-based, or both. And so this figure on the right, this represents those modeled scenarios, which is the probability of a reef having low, moderate, or high reef builder cover based on variations in scrapers and wastewater pollution, which is the X and Y axis respectively. The colors are the same as what's in the distribution plot to the left. You know, the salmon to pink to purple is the low, moderate, and high reef builders. And the lines, these are labeled, and they represent the probability of a given cover based on the values of scrapers and wastewater pollution. I'm just going to walk through a quick scenario. Is if we start where the star is, our sort of our initial conditions. If we start in a place with very little scrapers and really high wastewater pollution, we can see that reef has very little reef builder cover. It will be in the low category. But if we implement a fisheries management policy that promotes scraper biomass, we can see that the probability shifts and that a reef will most likely have moderate reef builder cover. However, alternatively, if we implement a policy that dramatically reduces wastewater pollution, but has no fisheries component to it, there is also a high likelihood that that reef will have moderate reef builder cover. And in fact, this land-based policy, actually, that probability of being in moderate cover is higher than the sea-based only policy. But importantly, if we implement an integrated management strategy, one that is both land and sea-based, and these measures occur simultaneously, our reef will have a high likelihood of having high reef builder cover. In fact, there's an 80% probability of having high reef builder cover, which means that the combined land sea management resulted in a 3 to 6-fold greater probability of high reef builder cover than if either management scenario were enacted in isolation. So taken collectively, our findings support really the need for reintegrating both land and sea within coastal ocean management, which is a central tenet of ecosystem-based management. And that's, you know, akin to longstanding indigenous stewardship of island ecosystems. A common thread throughout this presentation is this interconnectedness of island ecosystems, whether it's coastal and pelagic, land and sea, and of course, human communities are really an integral part within those connections. And you know, that is because deep sea connections between people and place are really a hallmark of communities here in Hawaii. For much of this seminar, though, we've largely focused on the drivers of ecosystem change. So, you know, talked a lot about climate and ocean drivers, and also human pressures that influence the status and trends in ecosystem health. But this really is only part of the story. You know, yes, our actions and activities certainly influence ocean ecosystems, but they also are the conduits through which we experience value and feel meaning and form identity. In that sense, the relationship between human communities and the ocean is more circular or reciprocal, and ultimately culminates as being critically important to human well-being. You know, admittedly, our report really only includes indicators on the top portion of this conceptual figure and largely misses the bottom portion. I will say the efforts led by Christina Leong, Jonathan Fisk, Alohi Nakachi, and others within our Science Center are really trying to make and are making inroads at this bottom portion. But you know, looking ahead, I think one of our grand challenges is to cultivate relationships and build trust with local communities, local practitioners, and so that we can better understand these diverse cultural connections between people and place. And I think only by doing so will this provide the best opportunity for success of ecosystem-based management in Hawaii. And with that, I'll just say mahalo nui loa again for being here, for attending the seminar, and I'll take any questions if you have any.
Jamie, thank you so much. This was a fantastic presentation, and really appreciate all of the work that you've done. I know that you have shared several several things that have links to them. So what I'm going to do right now is in the chat box, I'm going to paste a few links so that everyone can follow up with these if they want to. So we've got the Cumulative Impacts Viewer, the full ecosystem status report, and then a link to a story map for your nature paper. And so we're going to move on to questions in just a little bit. So if anyone has any questions or comments, please type those into the questions box now. And just a reminder that if you want to revisit any part of this presentation, we will have this up on the NOAA Central Library's YouTube page. And so we will have that available for you probably by tomorrow. All right, so we have one comment here, Jamie. What a great presentation. Thanks so much for sharing the report and the thinking behind the indicators and reporting. So thanks so much. And just a follow-up question to that, Jamie. We're wondering what was the biggest challenge for you in writing this report?
Well, good question. This is our first foray into going from West Hawaii to the main Hawaiian Islands. So I think, like I said, that was a pretty big shift in terms of spatial geography and then trying to be inclusive of the various sort of management desires and needs and requests that we were provided during our scoping. So narrowing down to the most salient indicators was really difficult, and collating that data as well. You know, I think some of these sections, I think we did a great job, and others we have missed. You know, I think we've largely missed any indicators related to protected species. I think that's something that we want to focus on in the future. So I think it was just it was a big learning curve that we're still undergoing, but you know, I think it's a needed evolution that we're trying to accomplish.
Agreed, and we do have another compliment for you here. This is amazing work, and it's a huge accomplishment. I absolutely agree with. I have one of my own questions, actually, Jamie. I know that you mentioned a couple of times during your presentation the intersection of Indigenous knowledge and stewardship of the land, and the way that ecosystem-based management is moving forward today. And I'm wondering if there are any specific paradigms that you think will be especially important moving forward.
Oh, that's a challenging question, and I wish I had Kirsten Leong or others on this to be able to chime in. You know, I think that sort of the historical Indigenous ways in which Native Hawaiians and sort of, you know, participated in and looked at resource management really influenced the ways that we thought about sort of that work in the nature paper, for example, is thinking about it from a more integrated approach. And so I think looking at things through that lens I think will be critical for us moving forward. But I think we still have a lot to learn. You know, I think we try and take our contemporary management practices and apply it in ways that might not make sense from a cultural perspective. So I think the more that we can learn, again, from local communities on the ways that we should think about, interact with, and potentially manage ecosystems will only help us and improve sort of you know, our management practices and the way that NOAA and the state and others think about the future of ecosystems. So it's kind of a punt on your question, but I think there's some important things for us to learn before we can move forward.
No, yeah, I think that's awesome. Thank you so much for taking a crack at that. I know that was a complicated question, but it's very much appreciated. And as you were talking, we just got just a bunch of questions come in. So the first one we have here is, if you could deploy an instrument to collect any type of data in the near shore to improve your understanding of ecosystem function, what would that be?
Wow, I'm interested to know who asked this question. Interestingly, we actually are currently, as I speak right now, we have a couple of autonomous vehicles collecting data on phytoplankton biomass in the nearshore environment in places that we've been unable to collect data in the past. And that information will be pretty critical for us to understand the spatial variation in primary productivity and help that will help ground truth and really serve as input towards ecosystem modeling of fisheries and ecosystems. So we're doing it now, actually, and I think that's it is a game changer for us and pretty cool to be able to be here at my house speaking to you all while simultaneously collecting some really novel and cool data.
Great, thanks so much. And I think this might be kind of related, but this question says, what are the biggest data gaps your team encountered?
I mean, I think the data gaps span from oceanographic to ecological to human dimensions. I would side on the human dimension side, though. I still, like I said, I think we have a lot to learn in terms of framing, and especially if we're going to talk about representing indicators of cultural connections or cultural ecosystem services, or whatever the terms we want to use. I think once we do that and we start to crack that nut a bit, I think that will help frame the entire report. And so it'll be interesting to see the evolution of the reports over time, and how the more we learn on the cultural side and human connection side, that, you know, the more I think our indicators may shift as well.
Great, thank you. All right, the next question we have, oh, we just got a bunch more come in as you were talking. All right, so next question here, this says, great presentation, very educational, I agree. Do you have any satellite-based data in your analyses, such as ocean color?
Good question. Ocean temperature and other indicators are all remotely sensed. In this report, we actually didn't include, although we have in the past report, indicator of chlorophyll, even though I talked about the importance of it. And I think that certainly will be included in future reports. So yeah, I think there's a mix of satellite and remotely sensed products as well as modeled products. And obviously, you know, some of these sort of synthesis products, like the downscaling, was, you know, satellite SST was critical for the downscaling the climate model output and projecting the annual onset of severe bleaching. So short answer, yes, although I think there's room for growth, definitely.
All right, great. The next question here says, how many of the indicators rely on quote unquote evergreen data from annual surveys or remote sensing versus less regular monitoring?
Can you repeat that question again?
Yeah, so this says, how many of the indicators rely on evergreen data from annual surveys or remote sensing versus less regular monitoring?
Oh, I mean, I guess it's like, what do we suggest as regular monitoring? So the NCREMP, the National Coordinated Monitoring Program, they do their best to get around Hawaii every couple of years. You know, the longer the time series, the more that becomes regular. But I wish that we had that data more often, and I'm sure they wish they had the ability to collect it more often. So it's a mix. I couldn't tell you off the top of my head the proportion of indicators that fall into one bin versus the other. I think we could use more data for each of these. There's no question. Even the satellite data, you know, talking about ocean color, you know, it's really cloudy in Hawaii a lot. So there are huge data gaps, specifically in certain areas that we just don't get information from satellites just because of that cloud formation.
All right, thank you. The next question we have says, is there movement on how the science can or will be applied to local and state management? And if so, what are the challenges being faced in implementing policies?
There's a two-part question. I think one is, I'll sort of reframe it as, you know, are these data sets and the information we're putting out, has it been used or is it useful for management? And I would say absolutely. A lot of the data layers, whether it's the cumulative impact layers, for example, those are being used specifically in two different ways. One, for the state, these are underlying a lot of their mapping along with some other products and other agencies, but those are all coming together to help inform their current push towards spatial management of herbivores, for example. And so again, understanding where you have either the most impacts or the least or whatever has been very helpful for them. I had a conversation with Jerry Davis of Habitat Conservation Division, and he suggested that a lot of these layers and information are also helping inform the EFH consultations. So there's definitely ways in which these data sets are being used. I think it's harder to point to a very specific policy in which our data has directly informed or changed. I think that is ongoing. Policies don't change, you know, overnight, and don't change very rapidly, as we know. So I think they're really informing the ways that managers think about the decisions they make, and that's, I think I'm optimistic that that will also translate into the decisions that they're making.
Great, thank you. The next question we have says, of course, more monitoring and data are critical, but do we know enough to take more aggressive actions to protect system integrity? And the second question says, is this a data problem or a problem of taking action and all that comes from that?
Yeah, I mean, I think our recent paper clearly shows that management action, integrated management action, makes a difference. I mean, I think it absolutely shows that. So I think, you know, the level of action and what action is needed and where is a different question, right? But I think that, you know, if we look back at we're talking about coastal ecosystems anyways, and we look at back where we have some of these, the highest cumulative impacts, but look at what the underlying drivers are, whether they're land-based or are they fisheries-based. So I think it depends on your purview as a manager, whether you know, is there an opportunity to affect both? Because I think we can implement a ton of marine management. We can you know, we can carve out areas and just exclude fishing altogether. But if we don't deal with wastewater pollution, we don't deal with sedimentation, and we don't deal with these other things that compromise water quality, then, you know, we're never going to realize our ocean conservation goals unless we're really coordinating and you know, approaching management from a more integrated way. So I think that was the answer to part of it. I think I've forgotten the other part.
Yeah, I think that was a great answer. We have a couple minutes left, and so we have one more question here. And this says, if you could tell leadership one thing to do more of, and not just get more money, and this is related to approach or directions here in this ecosystem and in other coastal ecosystems, what would it be?
Oh wow, my one wish to talk to leadership. This is it's a lot of pressure on the spot here. It's tough. So I don't know if this is my one wish, but it certainly is a wish. I think that there are a lot of great people in NOAA Fisheries and NOAA in general, but you know, I can certainly speak to NOAA Fisheries and the Pacific Island Fisheries Science Center. They're doing really incredible work. And I think that there is lots of opportunities for synergy, but it is difficult. There are barriers to sort of capitalize on that synergy, meaning for us to work together and for us to really, I think, focus our attention on what's in front of us. And that's a, you know, clear change in ecosystems and the desire and need and requirement to do the science and make hard decisions. And so, you know, I think promoting both within our agency, working together, but also really enforcing the importance of talking to local communities and getting out there and interacting with local stakeholders and individuals and people that have been here for generations and family that have been here for generations that really have great observations that can help inform what we do and how we do it. So I think it's both looking internal and also really driving home the importance of external connections and communications. So to sum it up, it'd be communication.
Jamie, thanks so much. That covers all of our questions, and we are right at the top of the hour again. So I am just going to pass this over to Peg Brady to wrap us up today.
Thank you, Shannon, and thank you, Jamie. That was a very powerful and wonderful presentation. Thank you so much. And that last question was something that I had in my mind, so I think you really did a great job highlighting that. So thanks so much for all the effort, and to the rest of your team, thanks to them out at the Pacific Island Fisheries Science Center. Thanks so much. And please come back and join us on January 10th to listen in to our next seminar in the beginning of 2024.